This is section 11.1, Introduction to Sequences. Our objective for the day is I can identify, graph, and identify terms of an arithmetic and geometric sequence. An arithmetic sequence is a set of numbers in a particular pattern in which the difference between consecutive terms is constant. Each number in the sequence is called a term. Sequences can be finite, like the example that I have here. This is showing something that has a starting point and an ending point. They can also be infinite, and you'll often see 3 dots indicating that this isn't finished, this is going on and on and on. A sequence is a function in which the domain consists of natural numbers and the range consists of real numbers. We talk about the symbols that you could see, talking about the domain, and talking about the range. For the domain, we can see that n is something that we could use, and for the range, we're going to use a sub n. We have some examples of finite sequences, infinite sequences, and the domain and the range of each. In an arithmetic sequence, each term is determined by adding a constant value to the previous term. This constant value is called the difference. Looking at the question, it says, what is the common difference of the following sequence? So we have to figure out how much are they adding to each number to get the next number. And we know to get from 3 to 6, we would have to add 3. To get from 6 to 9, we'd add 3. To get from 9 to 12, we'd add 3. To get from 12 to 15, we'd also add 3. So the common difference is 3 because that's what we're adding each time. In example 1, we're going to be identifying if the sequences are arithmetic. So the way that we do that, in order for this to be arithmetic, they have to add. We have to add a constant term between each of the terms that they give us, and then it's going to be arithmetic. So if they're doing something besides adding, such as multiplying, then that's not going to be arithmetic. Also, if they add 5 one time, but then they add 3 the next time, it's not going to be arithmetic. So let's go ahead and take a look at example 1. So to get from 5 to negative 6, if we think about how we do that, we know that to get from 5 to negative 6, we would subtract 11. And you might go ahead and think, okay, well this isn't arithmetic because we're subtracting and not adding. However, we could write our problem as 5 plus negative 11 equals negative 6. So technically, it's going to be arithmetic if we are adding or if we're subtracting, because we can always write a subtraction problem as an addition problem with just plus negative. So this doesn't automatically rule this one out. So let's go ahead and see what we do from get from negative 6 to negative 17. And if we go from negative 6 to negative 17, we know we're also going to be subtracting 11 or adding negative 11. And to get from negative 17 to negative 28, we'll also be subtracting 11 or adding negative 11. So this one is going to be arithmetic. Let's go ahead and look at the second one. To get from negative 4 to 12, we would be adding 16. Now we need to look and see to get from 12 to 28 what we would do. Again, to get from 12 to 28, we'd be adding 16. Now we want to see, okay, how many are we adding to get from 28 to 42? And here, to get from 28 to 42, we know that we're only going to be adding 14. So this is not arithmetic because it does not add a constant every single time. In example 2, we're actually graphing an arithmetic sequence. So first they gave us the sequence 10, 6, 2. And first we need to figure out what that common difference is. And so we can see that to get from 10 to 6, we're going to be subtracting 4. Remember, subtraction is okay because we can also say plus negative 4. And to get from 6 to 2, we're also subtracting 4 or adding negative 4. So when they're asking us to find the next 4 terms, all we're going to do is subtract 4 to get the next term. So we have 2 minus 4. We can also write this as 2 plus negative 4. We're going to get negative 2. So negative 2 is the next term. Then we'll take negative 2 and subtract 4. we'll get negative 6. Now we'll take negative 6 and we'll subtract 4, and we'll get negative 10, which is the next term. And then we'll take negative 10 minus 4 and get negative 14. So those are the 4 terms that they wanted us to find. Now we can go ahead and graph all of these terms, so the 4 that we came up with and the terms that they gave us originally. Now in this case, x is going to be representing which term, so number of terms. So is it the first term, is it the second term that we're talking about, the third term we're talking about, and y is going to represent the value of the term. So let's go ahead and do this. Our first term, so where x is 1, the value is 10. So our first point will be all the way up here. Our second term, so where x is 2, is going to be 6. So we'll have our point here. Our third term is 2. Our fourth term is negative 2. Our fifth term is negative 6. Our sixth term is negative 10. And our seventh term is negative 14, which is actually off of our graph down here. Notice that when we're graphing arithmetic sequences, these are going to fall in a straight line. Another type of sequence is the geometric sequence. In a geometric sequence, each term is determined not by adding a constant value, but by multiplying a non-zero constant by the previous term. This constant value is called a constant ratio. So here, when we're thinking about this on this first example, we're looking, instead of what are we adding to get to the next term, we're thinking what are we multiplying. And in this case, we're multiplying by 4 each time. 1/16 times 4 gives us a fourth. 1/4 times 4 gives us 1. 1 times 4 gives us 4. And 4 times 4 gives us 16. So that's the constant ratio in this case, 4. In example 4, we're identifying the geometric sequences. We're determining if the sequence is in fact geometric. So we want to think about this. How do I get from negative 2 to 6? Well, I'm going to have to multiply by negative 3. To get from 6 to negative 18, we're wanting this to be negative 3 so that we can say it's geometric. And 6 times negative 3 does give us negative 18. And to get from negative 18 to 54, we're also multiplying by negative 3. So in this case, it is going to be geometric. Let's take a look at our second case. To get from 8 to 16, we know that we're multiplying by 2. To get from 16 to 24, we would be multiplying, but we would only be multiplying by 1.5. So since 2 and 1.5 are not the same numbers, we don't have a constant ratio here. So our answer is no. This is not going to be a geometric sequence. In example 5, we're going to find the next 3 terms of the following sequence and graph the first 6 terms of the sequence. So we want to think, how do I get from 32 to 8? And originally, the first thing that comes to my mind, I would think, okay, you divide by 4. However, we know that geometric is going to be multiplying. But if you think about it, you can take 32 and you can divide by 4 to get 8, but you can also take 32 times 1 over 4 and get 8. So since we can write this as multiplication, then we can also say that if we divide to get to the next term, then it's going to be geometric. So now we know that to get from 8 to 2, we're also going to divide by 4. So to get our next term, we want to divide by 4. So 2 divided by 4 is going to give us 0.5. And then if I take 0.5 and divide by 4, I'm going to get 0.125. And if I divide 0.125 by 4, I'm going to get 0.03125. So when they're asking for the next three terms, these are our next three terms, and now we're going to go ahead and graph them. So x is still going to represent which term we're looking at, and then y is going to represent the value of that term. So our first term is 32, which is like way off of this chart. So maybe like way up here somewhere. And then our second term is 1, 8. Our third term is 2. Our fourth term is 0.5. Our fifth term is 0.125. And our sixth term is 0.03, which is almost down to 0. And if you notice, this is not going to be a straight line. There's going to be quite a curve in our line when we're graphing geometric sequences. In example 6, we're determining whether each sequence is arithmetic, geometric, or neither, and we have to tell why. So looking at example A, I need to think to myself, how do I get from 16 to 24? And I always go ahead and check for arithmetic first. So here I know I'm going to be adding 8. And so then I want to check, okay, do I add 8 to get from 24 to 36? And I know to get from 24 to 36, I would actually be adding 12, so that we know this one isn't arithmetic. So now we want to check and see if it's geometric. So if I'm checking to see for it being geometric, I know to get from 16 to 24, I'm going to have to multiply by 1.5. So I check, and then 24 times 1.5 does give me 36, and 36 times 1.5 does give me 54. So this one is going to be geometric. And the reason that it's going to be geometric is because we multiply by a constant of 1.5. So let's go ahead and look at example B. Again, I'm going to check for arithmetic first. I know to get from 1 to 4, I'm going to add 3. But I know to get from 4 to 9, I'm not going to be adding 3. I'm going to have to add 5. So now I'll check and see, okay, is this geometric? To get from 1 to 4, I know I'd have to do 1 times 4. So I want to check and see if 4 times 4 gives me my next number. However, 4 times 4 does not equal 9. So this one is neither. And our reasoning, which I'm not going to write it here, I'm just going to tell you, is because we're not adding by a constant or multiplying by a constant. For example C, again, I'm going to check for arithmetic first. So I want to see, okay, am I adding something to get from 23 to 17? And I know that to get from 23 to 17, I'm going to be subtracting 6. But remember, it's okay if we subtract, because we can also say that that's plus and negative. To get from 17 to 11, I would also subtract 6. And to get from 11 to 5, I would also subtract 6. So C is arithmetic because we add a constant of -6.